Good morning to all of you. My name is Mr. Govind Singh. I am Assistant Professor of Physics at Department of Physics and at Government Degree College, Dharamsala. So now in this lecture I am going to talk about what is dark matter. So this dark matter is basically an unknown luminous matter with almost no interactions with other particles except gravity. Means it does not interact by means of nuclear force and by means of electromagnetic force. So if it does not interact by means of electromagnetic force, so thus we cannot see it, so therefore it is known as your dark matter. And also it contains more than the 80% of the matter of content of the universe, and it present all across the galaxies, galaxy clusters and superclusters. So and it is also responsible through the you can say that the matter condensation. So this results the formation of galaxies, galaxy clusters and superclusters. So this is the energy budget of the universe, and this figure is contained in the Planck's, and this is the satellite based experiment, that is Planck's experiment, and these are the 2015 results. And according to these results, the 60% of the energy of the universe is consist of your dark energy, and we does not have any clue about this percentage of your energy. And 27% is your dark matter, uh, about which we are talking about, and 5% is your visible matter. And this 5% of visible matter contains all the galaxies, stars, planets, supergalactic interstellar space, galactic clusters. All this contains the 5% matter, normal matter. So and now you can say that if we do not see the dark matter, how we can say that there are dark matter present. So now we are going to talk about the evidences of the dark matter. So this curve, you can say this picture or this graph is known as your galactic rotation curves. So we know that the circular velocities of the star at radial distances from the center of galaxy give the rotation curve of the galaxies. So thus a rotation curve of a galaxy is the orbital speed of the stars in a galaxy as a function of the radial distance of the stars from the galactic center. So now further if we discuss is that, so for a star in such a galaxy at a center R, the galactic center moving with the circular velocity Vr, we must have a gravitational force, because galaxy contains a huge amount of matter, so therefore there will be gravitational force, and this gravitational force is balanced by the centrifugal force. This is balanced by the centrifugal force. So this m in the subscript less than r is the mass enclosed within the radius r. So if the star is within the dense central region of the galaxy, then this m less than r is equal to 4 by 3 pi r q rho, where rho is the average density of the central hub of the galaxy, means center of the galaxy. So therefore within the central hub of, one can expect that this your this rotational velocity is directly proportional to your radius of your galaxy. So thus in the figure, so from that formula, it as the galaxy we move from the central region to the galactic arm, there should be decline, because outside the galaxy there's supposed to be no normal matter, and therefore this rotation of the rotational velocity of the star should be decreases. But when we plot the data, exploited this data, so this after the center and after the outside the galaxy, this is a flat line. So you can say that the galactic rotation curve of the galaxy is your flat. So this can be due to the presence of dark matter. So and another evidence is your gravitational lensing. So you can say that this space-time fabric is your distorted by the gravity of your this galaxy. So therefore For due to this gravitational lensing, instead of one image, there are two galactic images of your galaxy clusters. So this phenomenon is known as your cosmic galactic gravitational lensing. So what should be the properties of dark matter? So first one is it should be neutral. It should be non-luminous because it does not emit electromagnetic radiation. It must be stable among the cosmological time. It should interact gravitationally, very big interaction with other particles, and the dark matter has to be massive. So there are various types of dark matter. On the basis of the mass and the speed of dark matter particle, it is of three types. First is hot dark matter. When the dark matter particle moves with the relativistic speed, that means a very high speed, its mass is less than the temperature of the universe at the time of decoupling. So this type of matter is known as hot dark matter, and neutrinos are the potential candidates of hot dark matter. Another type of dark matter is cold dark matter. So when the dark matter moves with the non-relativistic speed, means it moves with a very small speed and it has a mass greater than the temperature of the universe at the time of decoupling. So that is known as a cold dark matter. So example of cold dark matters are axion, weakly interactive massive particle, which is known as WIMPs, MACHOs, that is massive compact hollow objects. These are the few examples of cold dark matter. And another type of dark matter is warm dark matter. This type of dark matter is intermediate between cold dark matter and hot dark matter. Sterile neutrinos are supposed to be the potential candidates for dark matter. Sterile neutrinos are the fourth right-handed neutrinos, and they interacts very weakly. So if we talk about the hot dark matter, the neutrinos are potential candidates for hot dark matter. So there are certain properties of neutrinos. They are most abundant particles in the universe of the photon. They belong to the family of leptons and have spin 1/2, carries no charge, initially known to be massless, but recently in the neutrino oscillation experiment, they are claimed to be massive. They interact very weakly and gravitationally. It does not interact by means of electromagnetic force because they are leptons. There usually comes in three flavors: electronic neutrino, muonic neutrino, and tonic neutrino. Due to the various experimental anomalies, another type of neutrinos came into existence. These are stellar neutrinos. They are fourth states of neutrino. They are right-handed neutrinos. Stellar neutrinos interact by means of gravity and non-weakly. In neutron oscillation, stellar neutrino mix with the active neutrinos. So this is all about this lecture, and thank you very much.